All right, today we're starting with chapter 4, pumps or creation and control of flow. So the creation, that's the pump part, and then we'll talk more about valve. We already actually started this control discussion of fluid last time when we did the hydraulic valves and also when we did orifice, as we see here in this picture. Okay, so we will go over the different types of pumps. We'll start from the general category. So we will categorize pumps, and then we'll go over some examples of pumps that we will be using. And the control of the flow, we will be discussing how we can control the flow, not just the valve itself. We already discussed that, but we will be discussing, for example, what's the best position where we can increase the performance of the cycle. We will also go over P-compensated pumps. If you recall, what's that? The pressure compensated pumps. And usually that's with variable displacement pumps. We'll talk about variable and fixed today, and how we can take some feedback from the system. And then that's where we'll be discussing how we can control the flow. Okay, so first the classification or the different categories, how we can classify pumps. We have two main categories. We have first the dynamic pumps, and then we have what we call the positive displacement pumps. The dynamic pumps, the main function for them, for example, the water pump inside engines, inside cars. The main reason for which is called the coolant, if you want, or the water. Uh, it's the main reason for or function for these pumps is to circulate the fluid, the water inside my system in order to cool it down. It's not meant to push, for example, a piston cylinder to push a load. So that's why these are called non-positive displacement pumps. Okay, another example is the swimming pool. We already discussed this in previous courses. I don't know if you recall it or not, but for swimming pools, again, I'm not interested in having a high pressure at the exit here. Let's see, where's the return? That's the return. So the return means it's returning to the pool, it's not going back. And here we have what we call the skimmers. Usually these are one or two. Usually have a skimmer box. That's where the water goes back or actually pulled by the pump. So if you follow these lines, they should go back somehow to the pump. Yeah, it goes up behind this line. So it's coming like this, intersects, and that's probably the line coming back from here. It comes to here. But anyway, so it's gonna be pulled by the pump. So the water gets pulled back by the pump. It comes to the pump, and then the pump needs to push that water through the filter, the heater, whatever other system, and then overcome the friction in the supply lines. These are called return lines now because it's going to go back and to the pool, and that's why it's called the return lines. We also have drain lines in addition to skimmer boxes. We're not going to design a pool, so I will just leave it. But in general, we have some water being pulled by the pump. It filters that, it heats that, and then it pushes that back to the pool. So all what this pump needs to do is overcome the losses or the pressure drops in the system, which are in this case the filter, the heater, and the friction inside pipes. Okay, so again, it's not meant to deliver high pressure when it reaches here, the return. Probably I needed enough to exit here and just create some kind of circulation so that it can reach back to here, in addition to help the pump suck the water back. Okay, so why I'm mentioning all that, well, this pump is not meant to, again, deliver, push a load or provide high pressure, and that's why it can be categorized under the non-positive displacement pumps or the dynamic pumps. Okay, so they're not used for high pressure applications, these pumps. That's why in our discussion we'll be mainly talking about the positive displacement. I can't recall what we did in fluid power, but I believe we did piston pumps, vane pumps, and gear pumps. Okay, and that's what we saw here in the on this slide. That's a gear pump example, or it's just a sketch for gear pump. So positive displacement, then, these are pumps that are meant to provide us with higher pressure or higher pressure at the exit compared to the inlet. How they work, usually we play with the volume inside the pump. We tend to start with a larger volume and then we squeeze that volume so that when it exits, it's at a lower smaller, maybe much smaller volume. And we'll see those in the examples. Uh, yeah, in the coming slides, we'll see how the volume actually changes from large volumes at the inlet to smaller ones. So once it's smaller, it's gonna pressurize them so it exits with a higher pressure. An example as this hand pump. We see those in parks, for example. It's like the handle. What you're actually doing, you're pulling this piston back. And if you notice that that's, for example, the tank, the well, whatever, that's the reservoir where the water is, and that's my output from the system. If you notice, we have two check valves here and here, and those are the ones that control that pressure in the system. We'll see some other systems as we go. So what happens once you pull it back, if you pull the piston back to this position, now I have all this volume. You pull that piston, notice that this check valve doesn't allow flow to go this way. So nothing will move from right to left here. What happens is you're creating vacuum right here. Depending on the pressure at the source, so there will be pressure difference between here and here. So there will be enough pressure to open, to crack this check valve, and then the fluid will start flowing in this direction to fill this volume. Now, when we start pushing on the piston back, start moving this way, no water or no fluid can go this way. And until I reach, so I would adjust this pressure to the pressure, the delivery pressure that I'm intending to do. So as long as we don't reach that pressure, the water or the fluid here will be pressurized until we reach to that limit that I'm looking for. So once we reach that limit, this valve opens and then water or fluid will start flowing in this direction. Different types, actually, not just these three, but those are the ones that we'll be discussing. We'll be focusing a lot on piston pumps. The textbook has a nice performance comparison between different types. I think they have the G-rotor, vane, and let me see here. I don't have it in the slides, but if you're interested, you can check the different performances. Some of them, they are meant to okay, let's see. That's the G-rotor pump. gerotor, vane, and axial piston pumps. So they're looking into the performance for these three different types of pumps. And we'll check what's the gerotor if you're not familiar with. We did in fluid power, MET 230, we did actually the gerotor motor, if you recall. We did that and the piston. So the motor is essential. It's the same as a pump, except it receives fluid and it deliver higher fluid through the shaft. So you deliver mechanical, and then we convert the mechanical into hydraulic power. Whereas motors, they take hydraulic power, so they take pressure and flow, and they provide mechanical power out. So we have the gerotor and then the vane. I recall also I had one for the gear. I can't find it on my slides. Maybe we'll see it as we move. And then axial piston. So if we have axial piston pump, then we do have another type of piston pump. Anyone remember or is familiar with another type of piston pump? If we have axial, then we have something else. My volume up, yes. Anyone? So we have axial piston. We have another one, which is also, it's very common for piston pumps. Radial piston, anyone heard of that? All right, we'll see it as we move on these slides. All right, the first one we want to discuss is gear pumps. Again, we'll be only discussing not fixed, positive displacement pumps. We'll start with what we call fixed displacement pumps. What fixed means, that means the output here, the output at any pump of those fixed displacement, which are mainly the pressure and flow. That's my output, are constants. They don't change. What I mean by that, so if you buy a pump that has, let's say, 15 psi and 5 gallons per minute, that's it. You can't change it. Even if the load is changing, you need to do something, you can't change that. We did discuss this in the previous chapter when we were discussing valves. We said when we have fixed displacement pumps, then let's say I want to control the flow. It's that example where we had a pump and uh, a motor, and we needed to control the speed of the motor. So we had to provide a needle valve to control the flow. So that's what we mean by fixed. So the first example we want to discuss is the gear pump. From its name, so it's made up of two gears. One is connected through it's very bright. So one is connected from here through the shaft into the motor, and that's the one that drives here. So you have the electric motor, it drives one of the gears mostly. And then this gear is just connected through like bearings. So it's installed there, it's fixed there. So the red one will be driving this, and then this action, as they move, they're going to create some kind of lower pressure or vacuum here compared to what the flow is coming. So it starts pushing in, it starts pushing or pulling the fluid through here between the gears and the enclosure. And as it moves, it's going to be pressurized, and it leaves the system here at a higher pressure. This type of gears, if anyone recalls from previous courses, they come with a higher rate of leakage. Okay, and where's that leakage? We do have some kind of, it's kind of like intentional to leave some clearance between the gears and the enclosure here so that we don't have high friction rate, and that allows some fluid to flow back. Also, if you notice here, we have too many arrows now. If you notice, when it reaches the output, the gears actually, they go back. So some fluid will be drawn back, and that creates, so not all the fluid, let's say we have 5 gallons per minute coming in. We're not going to deliver 5 gallons per minute out. We'll be delivering, let's say, 4.5. So that difference, we don't mean like leakage, like we're leaking the fluid out uh, outside. That's something else. That's like the enclosure is broken. No, it's causing some kind of leakage internally. So the fluid goes back and then it gets pulled. So we're not delivering what the pump is designed for. Okay, so it has high leakage. They are actually not that expensive compared to other types. So there is some kind of balance or optimization that we need to check, like how much do I want to pay versus the efficiency. I'm not sure, but let's see. The mechanical losses. Also, that's when I say we have nice comparison between the different pumps. So they're showing you for different speeds and pressures, the comparison between the different. Yeah, I don't have gear pumps here. Okay. Okay, so this is the first efficiency. If again, if you recall, we're reviewing those. So that's called the volumetric efficiency. And it's equal, if, Q is the volumetric flow rate. So that's the actual, when we say pump, so we're delivering flow. For motors, we take flow in. So for pumps, how much I'm actually delivering. So that's the actual flow rate divided by the theoretical, the design value uh, that we calculated or we designed this pump. So anytime we use the equations that we'll see later on for the flow rate, that's the design value or the theoretical flow rate. The actual value has to be either given to you, or in general, when we say given, it has to be measured experimentally. So they would tell you, we measured the speed and we measured, let's say, the area, the velocity, and the output. So you can calculate the actual flow rate. Or they will explicitly say it, hey, that's the actual flow rate or the measured flow rate. So if you see measured, that's the actual flow rate. Then you have to calculate the theoretical, and then you can find the volumetric efficiency. Okay. That's the first type. The second one is the G-rotor pump. It's made up of, again, 2 gears, except those 2 gears are, you have an external one and then you have an internal gear. If you count the number of teeth, this one, two, three, four, five, six, it should be less than the number of teeth for this. That's 1, 2, 3, 4, 5, 6, 7. This difference between the gears is the one that allows you to create that change in the volume between the inlet and the outlet. We will design it so that as we move toward the outlet, we're going to squeeze, we will reduce the volume and we will squeeze the fluid so that once it exits uh, the outlet of the pump, at the outlet, it would be at a higher pressure. Okay, the inlet, the volume is large. As it moves, the volume is decreased and thus pressurizing the fluid as it exits. Okay, that's the second type. The third type, we have the piston pump. What we see here is a axial, that's the axial piston pump. From the name, axial means the pistons are moving axially. So what happens as this is called the swash plate. And here we have, if you're looking from the side here, so that's what you see. So one slot here, one opening will take the fluid and the other one will be leaving the system. And then here we have the shaft. It's going to rotate. So if we only have one, as we see here, As it rotates, it goes down. It would be here. Again, this is, I believe that's the fixed, so we're not changing that yet. So as it moves, it has to push the fluid. So the exit volume, you should see it here. So that's the inlet flow here. So it goes, you see at the outlet how the volume is actually decreasing. So it would pressurize the fluid, so it leaves at a higher pressure. Okay, that's if it's fixed, then that's all what it would do. If we want to have a variable displacement pump, then this wash plate starts moving by changing that inclination angle. Uh, Ultimately, if you reach a point, it would be in the opposite direction. So it would flip what the inlet is and what the outlet is. The piston pump and piston motor, it's essentially the same, except the fluid would come in at a higher pressure. So it would push the swash plate. There's no other place to go except to turn that swash plate so that the fluid can exit. Okay, so it's the same construction. Nothing is happening except here you have this shaft is turning and it takes the fluid so that it pressurizes that and it leaves at a higher pressure here at the outlet. Whereas in motors, we have high pressure coming in. It rotates the plate, the swash plate, and then it rotates the shafts, thus delivering mechanical work out. And then it leaves at a lower pressure. Okay, I think I have a video and 3 slides. So now let's check the variable displacement pump. As I said, the swash plate is set to a fixed angle and it doesn't change. The shaft turns and then you have a fixed volume here and a fixed volume output. So my output from the pump is fixed pressure and flow. If I need to have variable, then I should start changing the angle of that swash plate, whether I change it manually or automatic through a solenoid valve or some other kind of type of mechanism. Uh, the idea is to start changing that, and then I can change I can control the inlet and outlet volume in general, the outlet volume, so that I can control how much I pressurize that fluid. Okay, if you need to do nothing like the neutral, then it would, as we see here, that's what we have. So the inlet and the outlet, they have the same volume. So the fluid would just go in and out as it's just rotating. It's not delivering any pressure. So that's kind of like the neutral case. Let's check this video here. Let me know if you hear the let's see if it works first here.
The variable plunger pump is the driving force for the motor and other actuators.
Do you hear the volume? Is the volume okay? I mean, or do you hear the
Yes, it's
sound?
good.
Okay.
Which highly pressurizes and delivers the drop forward. Shaft, cylinder lock, plunger, swash plate, valve plate, and other components. Shaft rotates. Plunger strokes along the swash plate, sucking into the main drop oil.
So next they'll start talking about P-compensated pumps, or in general how we can control that swash plate depending on the load, the output load, if it changes how it can control that swash plate. So if you want to come back to this video, do you have the link on the slides? Did I give that to you? Anyone? Do you have the link in the video, in the slides, the link for this video? If not, I can share it with you. So if you want to come back later and watch it, because we're gonna do P compensated or pressure compensated pumps later. So I don't want to watch that.
I'm not sure
Well,
if it is because my slides are printed out.
okay. Yeah, I'll provide that. I thought I did. Usually it might be hiding under this. Of course, you can't move it because you have it as PDF. All right. So now we have the third type. I don't know. We have a lot. We checked the gear, the G-rotor, that's the fourth type, or if you want the third type, it's piston, but now that's the radial. So that one, since the pistons, so how we categorize these piston pumps, it depends on the motion of the pistons with respect to the system. So we saw here the pistons are moving, although the swash plate is rotating, but the pistons, the action of creating that uh, change in volume, the pistons are moving axially. So that's why it's called axial piston pumps. This type, we have a casing and we have some uh, like chambers here. And then we have a camshaft, which is eccentric. So it's not like two circles. No, it has to have some kind of eccentricity. And that's actually how we can control how much we can change that pressurization, because the more you move it, then you're going to have a smaller chamber here at the outlet, so it would be pressurized more. And the textbook actually, for the next one, for the vane pump, it does show you how you can adjust, because the vane pump is very similar to this type. So what happens here as the camshaft rotates, these pistons, they start moving in and out. So they start taking, I believe, suction. That's the suction because it's the largest. And then as it rotates, this would be the outlet. So it's the smallest volume. So it would be pressurized to, it might be moving this way. I don't know. Do they have, yeah, that's the rotation because that's the pressurized. The vane pump is similar to that, so that's why I'm gonna only show this video. It serves for both the radial piston or the vane pump. The vane, it's just again, it's very similar to that. You have a camshaft, except now the slots are inside. Let's run the video as I talk. The volume here, it's inside the cam, not inside the enclosure. As you as the flow goes in, the volume is actually reduced here at the outlet, and then it leaves with a higher pressure. We need to maintain these chambers, these volumes, so they have to be sealed. Otherwise, the flow would go down. How do we do it? If you look here, that white here, this white stuff, it's either a fluid, a pressurized fluid. So as the pistons move and they tend to push it back, so they keep that seal between the vanes and the enclosure right here. This could be a fluid or some kind of material, or it could be a spring. So it pushes the vanes, so the blades, so that they stay with the enclosure. Let's see, controlling here, the rotation speed. Yeah, so if you control the rotational speed, then you're actually controlling how much volume you're having out, the volumetric flow rate out, because it would be slower. If you recall, Q in general, the volumetric flow rate. It's the volume times the area, the velocity times the area. So if you're looking here at, I know I can't try here. So if you're looking here, that's the area that the fluid exits. So if it's lower, then the volumetric flow rate would be less. The equation for pumps and for motors for the volumetric flow rate, it's N times the displaced volume. That's it. The rotational speed, RPM. I have it, so you don't need to write it now. We'll actually, I can just do this. So the volumetric flow rate, it's the RPM, the rotations, times for any type, times what we call the displacement volume. So the displacement volume, it's how much we're getting out through one rotation. That's why it's cubic inch per revolution. Forget about the units for now. We'll discuss it in just a minute. But it's giving me, for example, for what's the displacement volume for gear pumps? Let's put it here. So if you have, actually, let's go all the way back to the gear pump. So the displacement volume, it's these volumes. Can I pause it? No, I can't. It's just, so it's these volumes. So what's that volume? If you look here, assuming that's the gear, it's not the best, but trying. So it's this, and this. So if we assume it's kind of like of half between the gear volume and the empty volume where the fluid will be rotated, what's the total displacement for this gear pump? Remember, we have one here on the right and another one on the left. So I said if it's half, then the total would simply be like this. So it's this area here. So it's pi over 4 d square minus pi over 4 d square, or pi over 4 d outer square minus d inner square. That's actually the easiest one to calculate.
The videos also don't work.
Which one?
I think both of them. I checked on the slides and they aren't working for me.
Because it's PDF. I didn't upload the PowerPoint, so it's not going to work for you.
Yeah, I was just letting you know for a while ago.
Yeah, okay. Yeah, these are actually, if you go to that website, I'm not doing marketing for him, but he has nice illustrations, not just for, if you're on it, I don't know if, yeah, this doesn't want to go away. But if you look there, mekanizmalar.com, you're going to see probably another one. For that one, I did provide also the YouTube. But if you go to that website, they have nice illustrations. Yeah, that's the website right here. This is from YouTube, so I'm not on their website, so I can't click on here to take me there. It might, but I don't want to exit the slideshow. Anyway, what I was saying is the displaced volume for gear pumps, it's pi over 4 d squared, the outer square minus the inner square, or the outer casing minus the inner gear. So of course, that's just area. If I need the volume, then I need to multiply by the depth into, or what we call the width of the teeth itself. So that's what we call the teeth width, because that's the one that goes into the paper or into the screen. So times W, that's the displaced volume. We have other types. I won't go over them, but if we need them, then we're going to come here and calculate these. For example, for vane pump, it's pi over 4 d cam plus d rotor divided by 4 multiplied by the eccentricity. If you recall, we said we need to have some kind of eccentricity. So it's moving away from the center of the outer casing, or the outer casing, of course, times the width. The eccentricity could be calculated from this equation. For other types, we have it. I have to mention, these are the design values for the displacement pumps. For the displaced volume. What I mean by that, that's kind of like when the pump is brand new. over time, we'll start having some cracks, some precipitation on the enclosure, so that volume would change over time. So I wouldn't recommend using these equations. Instead, if you want to calculate the actual flow rate or the theoretical flow rate, but still, and compare it to the actual flow that you get out, we need to have that theoretical flow or the design value based on when I'm doing the measurement. So how do we do that? We did it actually in 230 in one of the labs, the pump. We take a couple measurements, and then what we do, we move all the way back when so I'm showing here the displaced volume versus, or actually the speed of the pump versus the flow rate. So I would move, I have this, I can't run with zero speed. So I would extrapolate this back into the zero flow, and I would read the speed, and then I can use the speed and the flow at any other point to calculate the displacement for each rotation. If it's fixed, then it's a fixed RPM and fixed flow, so I can calculate the displaced volume. So we can do that experimentally. We did it in one of the labs. If you still have the labs, go over it. If not, we can do it, or I can show it to you. There is a class running for 230 this semester, fluid power. So you can, if you don't recall, I can check when they will be doing that lab and let you know so that you can join them or just watch it or just simply upload that assignment for you. You can, that lab assignment for you. All right, let's do this. Oh, we didn't finish here. So now we go back to the units. Usually it's in English units. The displaced volume, it's an inch cube per revolution, and then multiplied by RPM. So that means the flow rate would be an inch cube per minute. If I need that to be in GPM, which is gallons per minute, all what I have to do is convert the cubic inch into gallons. And we know 1 gallon is 231 cubic inch, so we will divide the VD times N by 231, and then my unit would be in gallons. Since it's RPM, so it's rotations per minute, so I do have the per minute ready, so I don't need to do any other conversions there. Which one should I use? It depends on the problem that we're doing. So in this example, we have a gear pump that has a 3-inch outside diameter. So D outer, it's a gear pump, 3-inch, and the inside diameter, I'll just write it as D small. So that's D and D if you want. And there are two on both sides, but we said when we calculate the displaced volume, it's just pi over 4 D square, D outer square minus D inner square. And it has a width that's 1 inch. If the actual, so that's the actual pump flow is measured to be 28 GPM. So if the actual pump flow at that speed, 1800 RPM, is 28 GPM. So again, this could be if the measured flow rate, for example. So that means that's the actual. Here it was very clear, it's the actual. But if they say the measured, then that's the actual. What is the volumetric efficiency? The volumetric efficiency, it's the actual flow divided by the theoretical flow. We have this 28, so I need to find the theoretical flow. What's the theoretical flow? We said that's the design value, and that's what we get from the equation. This one in gallons per minute, so I need this one also to be in gallons per minute. I have N in RPM. I need to find the displaced volume. Probably it's going to be an inch cube because here we have them in inches, so I will need to divide. I'll use the second equation, this one. So let's first find the displaced volume. It's pi over 4 D outer square or minus D inner square. So it's pi over 4 3 square minus 2 square, so 9 minus 4, 5 pi over 4 times the width, so times 1. It's not going to affect if you forget that, but it is wrong, just in case the width is not 1. 3.93 cubic inch. Again, that's the this hashed area. We said that's per revolution, okay? So usually the displaced volume, that's the volume per 1 revolution. So how much volume you're doing in 1 revolution. And then per minute, that would be the volumetric flow rate. It depends on the speed, how fast you're going per minute. So Q theoretical would be N times VD divided by 231. So N is 1800. And then 3.93 cubic inch. It doesn't matter the units here as long because we're not going to cancel. This has to be an inch cube. This has to be an RPM. And since I'm dividing by 231, so that's the cubic inch per gallon. So we'll have gallon per minute as my answer. And I got here 30.6 GPM. It has to be larger than 28. If not, then don't continue. Don't just flip the numbers. Let's say you got here 26. Oh, so my volumetric should be, efficiency should be 26 over 28. I'm good. It's less than 1. Well, it's wrong. That's the theoretical. That's the design. Why do we have a difference between this value and this? Why there's a difference between those two? There is the leakage. So the difference between 30.6 and the 28, which is the 2.6, that's the leakage flow rate.
What would you say would be technically wrong? Did you say it would be that if you left out
If
the
it's
one?
if it's less than 28.
In the previous step, you said that the one wasn't necessary, but you said it'd be technically wrong. What was the one? The number one?
Oh, that's the width.
Okay.
I mean, it's not going to affect my answer here if I forgot that, but that's from the equation. Because if you just do pi over 4 d squared minus d squared, the unit here is inch square, so that's not a volume. So make sure that you put the width. I didn't write it here, so I said if you forget to put it, you're going to get 3.93. But it's not going to affect the answer because the width was simply 1. So, but
Oh,
if the width was half or 2 or any other number other than 1, then your answer would be wrong.
gotcha. Thank you.
Yep. So again, make sure that Q actual is less than Q theoretical before you continue. If it is, oh, so let's write here then. The volumetric efficiency would be 28 over 30.6, and that would be 0.913. That's my volumetric efficiency, or 91.3%. Okay. As we said, the difference between the 28 and 30.6, that's what we call the leakage flow rate. So that's because sometimes you will be given, let's say, this pump has a leakage flow rate this much, and that they won't give you the actual. What you need to do, you will calculate the theoretical, okay? And then you would actually find the actual flow rate from this difference, Q theoretical minus Q leak. Or they will give you the actual flow rate and the leakage flow rate. So you will have to say the actual plus the leakage plus how much it leaks. That's the theoretical value, because you might be missing, let's say, the volumetric displacement, and you will come back, hey, I can't calculate the theoretical value because I don't have the V sub D, or the displaced volume. Okay. Next, we have the second type of losses or efficiency. That's what we call the mechanical efficiency, mechanical losses. Where's the mechanical loss? It's actually all the way from here, all the way back to the shaft. So if you notice here, the shaft has bearings. So there'll be some friction. There is more friction here and here. So all the way from here to here, there are some losses, mechanical losses. And mostly when we say mechanical, that's due to friction. Okay. An equation for that, it's equations 4.5 and 4.6. It's the pressure times Q theoretical divided by 1714. Are you familiar with this? Anyone recalls what's that? PQ over 1714. We've seen it before. That's actually what we call the hydraulic horsepower for the pump. That's how much you're getting out from this pump. We used it a lot in the previous chapters. Now, we didn't say actual or theoretical here because we didn't do actual and theoretical. But, and then we have Tn over 63,000 or 6325. That's actually the mechanical power. So it's the hydraulic horsepower out, the theoretical one out, divided by the theoretical or the mechanical power n. If you use Q theoretical, that's the design. That's what gives you that's what define my mechanical efficiency. Again, this equation, those two equations, 4.5 and 4.6, and that's one of them. It's unit ready, so you have to make sure that you meet the units. The pressure has to be, as we said here, PSI, Q, and gallons per minute, GPM. The torque has to be in inch pound, not foot pound, and the N has to be in RPM. Okay, because we have these constants here. The 1714 gives me horsepower here, and then the mechanical power, it's Tn over 63,025. So this is also, once we put this torque in inch pound RPM, this will also be horsepower. So be careful. Now if we go back now, we have volumetric efficiency here, and then we have mechanical efficiency here. So from this point to here only, we're not going to discuss all the way back to the plug, because there are electrical losses and so on. But for the pump only, we have now what we can define the overall efficiency. So that's the total efficiency. For efficiency, the total would be the product, not the summation. Don't add. Efficiencies has to always be less than 1. You can't have an efficiency more than 1 or 100%. Okay, I'm gonna just say it. Let's say almost 100%, but you can't cross that. So if you add them, you're actually, let's say the volumetric was, in the previous one was 0.91 something. Let's say the mechanical efficiency is 85%, so it's 0.85. If you add them, you're gonna have a volumetric efficiency that's more than 1, so it's above 100%. That's why it can't be. What you should do is actually, you do the first one, the volumetric efficiency, and then that output is also going to be less due to friction losses by 15% from here. So the overall is actually the product of all the partial efficiencies. So if you have electric efficiency, then you add it here. If you have some other efficiencies, you just not add it, sorry, you multiply it by, I meant add it to the equation. So you keep multiplying those efficiencies. In this chapter, we're going only to consider the volumetric and the mechanical efficiencies only. And now you will notice it's actually the same equation as the mechanical, except the flow rate flips from being theoretical for the mechanical efficiency into actual flow rate and the overall. That's the only difference between the two. Well, if you have your mechanical efficiency as P, the pressure, times Q theoretical divided by 1714, and all that divided by Tn over 6325. And then that's my mechanical efficiency. The volumetric efficiency, we just defined it as Q actual divided by Q theoretical. What happens to Q theoretical? Simply drops out, it cancels. And then this equation, this would come to here. So you will get P, Q actual divided by Tn, and then the same equation, except Q is Q actual, not Q theoretical. So be careful. If you use Q theoretical, then that's the mechanical efficiency. If you flip that into Q actual, you multiply it by Q theoretical and divide by Q theoretical. And that's what makes the jump from mechanical efficiency into overall efficiency. Is that clear? So if you see me mix those actual flow rates, just let me know. Tell me, hey, you're not supposed to do that. It has to be Q actual for the overall efficiency. Another note here. So fluid temperature, also that's something that you need to consider when you're working with hydraulic fluid. It's unavoidable due to friction, it's going to heat up. So if you do a performance test, when you start the pump, it would be different than after running the pump for 2 hours, 14 hours, and so on. Also, we mentioned that when we did the labs for the pumps. Do you recall we used to record the temperature before and after? And the question would be, what do you expect to see if we started, let's say, after 2 hours? Or the question was actually, we were closing the valve so that we can control the pressure. We started from the low pressure, and then we started closing the valve as we move. So as you close the valve, then there will be friction. So by the time you're done, the temperature is higher. The question was actually, what happens if you started from the higher pressure and you went to the, so if you close the valve all the way and then you start opening, so it's different because the pressure is different, which heats up the fluid. And then what's the main effect? It's going to change the viscosity of the fluid. So that's something we need to keep in mind when we do this type of analysis. Let me see. I'm ready to start with pump performance, so we'll discuss that. Okay, so P-compensated pumps, as we said, before we go there, let's check a main difference between fixed displacement and variable displacement. As we said, fixed, it's going to give you just constant outputs, so constant P and Q. Whereas here, the pressure could change as the load is changing. Now, how that happens, we're going to see it in 2 slides from here, probably, if my notes are matching the slides. But since this is fixed, now let's say the load here is changing and I don't need that much, or maybe something happens down here. So fixed displacement pumps, they should always be accompanied by a pressure relief valve. Okay? Whereas variable displacement pumps, since they do change based on the output, let's say the output is less, it would send a signal to the pump, or the pump somehow it senses that the output is changing, then it can actually change or lower the pressure. So if anything happens, it should be able to lower the pressure. So it's not necessarily to have a relief valve, a pressure relief valve, but it's recommended. You never know. Maybe something happens, the pump doesn't sense, the variable frequency drive. That's what we install on pumps to change that speed based on the output load. So if it, for some reason, it's not working, then we want to avoid having we don't want to reach to the burst pressure that would explode the whole system and you start having some fluid leakage all over. So it's not recommended. I mean, it's not needed, but it is recommended to have it. And those are usually, we use them with P-compensated pumps. What do we mean by P? That's the pressure compensated pumps. We can't have P compensated, so it doesn't make any sense to have a signal coming from the load to the pump. So if the load decreases, okay, so what? This is a fixed displacement pump. It can't change the output. That's why sometimes I do ask that question. Do we need to have that signal for P-compensated pumps with fixed displacement? And that's actually right here. So P-compensated pumps, they are used to improve the efficiency of the pump with a change in the load by sensing that load and sending a signal to the pump so that it can adjust the output. And that's the second part of that video. Let's check this one. This, I like it. I should have, you should have this link. This is a link, by the way. So if you're not here, if I click, it would take you to the YouTube. Again, it's a PDF, so I don't know if it would convert that link to something that you can use. If not, I can always send it to you later. So what we have, if it runs, before he starts clicking. So we have here, you don't need that. We have the pump rotating here. That's the inlet. So it says from tank in blue. It goes in and then it exits as red. And you have, if you want to watch this, this is the green once it crosses the red. So he's going actually to play with this scale here. So once he crosses the red, that's something we don't want. So I want to make sure that the pressure remains below the green, this limit right here. So as it crosses, it's going to I can't hover over this because it's giving me this line, but watch this line back to here. So that's actually my signal. Here it's a mechanical signal, kind of like the fluid would go. So once it hits the red, then the pressure is high enough to push the spring back. As the spring is pushed back, what happens to the swash plate? It adjusts. Okay, so this is a mechanical signal that controls that swash plate. There is solenoid, which is electrical, so it sends a signal to a solenoid valve, so it opens and closes this shaft, or like it moves it back and forth, so it opens and closes or changes the degree of the swash plate or other types of pumps. So let's watch this quick illustration, animation if you want. Now he's increasing the pressure. That means the speed or the output should increase. But at one point, I don't know, they're not talking, so I'll keep just talking here. He's going to cross that limit. So the pressure red, or the red line at the output, would be times the area of retract, if you're looking from there, because that's where the shaft is. So it's this area should be larger than the force of the spring. What's the spring force? That's something that I would adjust so that it would give me that limit or that difference between the green and the red colors. Okay, is it clear?
I think so.
Again, all these, so that's actually the second part of that video that I skipped. I stopped it like at 1 minute, 7 seconds, but it's almost the same, except it's not mechanical, it's a solenoid. So it would send a signal to the servo, to the solenoid, and then it starts opening and closing, changing the angle of that swatch plate. Now, again, it's happening. Is crossing that limit, so it sends that pressure kind of, it pushes the spring, so it adjusts, and then it would adjust the output pressure. So those are called pressure compensated pumps or P compensated pumps. In order for us to be able to do it, then the pump itself has to be variable. That's why I can't have a P compensated pump with a like pressure relief with a decompensated pumps. Let's do example 2. And then next time we'll discuss flow control. I don't know if we can finish it today. Probably not. Let's see how much we can solve. All right, what we have this tank. It's slightly different than what you have. I did change the lines in and out into the cylinder coming. So we have to follow, we have the reservoir, it's vented, which means here it's atmospheric pressure. The suction pressure here at the inlet, that's -4 psi, and then the pump delivers a specific volume, which we don't have it. But let's move this up. We have here the pump running at 1800 RPM. It has a mechanical efficiency 90%. That's the pump, not the system, because they're going to ask for the system efficiency at one point. And the volumetric efficiency is 0.92. Let's see what's left. Maybe we'll do it next time. This would be the last slide. 32. Yeah, homework 3. All right, let's solve. Let's see till it's 11:20. We would deliver a flow rate here. It goes through the DCV, the direction control valve, and then goes up and then goes into the piston. Why the lines are important? Because when I need to check, is it pushing or pulling? So which one has the high pressure? Is it this side or that side? Because P times A, that's the force. Now the flow would come to here and then goes into here. It's going to move the piston at 3 inches per second. Okay, so now the piston is moving at 3 inches per second. The cylinder and bore, we're going to assume they're the same. It has a diameter 8 inch, and then the rod diameter in the back, it has 4 inch diameter. This shaft here has a diameter of 4 inches. The pressure drop from the pump to the blank of the cylinder, so from here all the way to here, it's 75 psi. That's the pressure drop. That's probably you need to calculate, but they give it to you. Does that include the DCV or not? If it's not given, then we're going to say yes. The pressure drop from the cylinder rod end to the tank, so it's from here all the way back to the tank. Otherwise, you will have to calculate this from, as we did in the previous chapter. This is 50 psi. First, we need to find the volumetric displacement of the pump, VD. How do we do that? So they didn't say anything about the pump. Is it a gear pump? Is it a vane pump? Is it some type of other pumps? They didn't say what's that. So I can't use one of the equations. They're already equate like pi over 4 d squared minus d squared. So the only equation that I can use is Q theoretical as VD times N divided by 231. I do have the RPM for the pump, so I need to find Q theoretical. I have the volumetric efficiency given, so my task now is if I can, because the volumetric efficiency is Q actual divided by Q theoretical. I'm looking for the theoretical flow rate. So if I can find, I have the volumetric efficiency given. If I can find the actual flow rate that the pump is delivering, then I should be able to go backwards. What's Q actual? We said it's either will be given and saying it's the actual or the measured. Do we have anything that's been measured? Yes, we measured actually the speed of this cylinder. The cylinder in this case, it's moving from left to right and we're pushing this 40,000. We're going to need it at some other points probably next time. But we're pushing the cylinder from left to right. So it's here. So the flow rate that comes from here, it's the same that goes all the way into the cap area of the piston. So Q actual, the measured, it's the velocity of the piston, V times A cap of the piston. Okay, if it's the other way, if it's retract, then it's A piston minus A of the rod. Okay, that's why I said it's important to know the lines, which one going in and which one is out. So Q actual is V piston, and that's all the way going back to the pump. So that's why I can use the piston delivery or the measured values for the piston. So what's the speed? 3 inch per second. And then the area is simply pi over 4, 8 inch squared. So this would be in cubic inch per second. If I divide by 231, I should get the answer. And actually, it's per second, so be careful. Let me see, pi over 4 d squared times 3. I'm going to divide it by 231. That would be in gallons per second. And then multiply it by 60. Okay, so this would be cubic inch per gallon. And this would be 60 seconds and 1 minute. So second with second, that's per second. And then inch and inch square will cancel, and then we're going to have gallons per minute. This would be 39.2 GPM. Okay, now the volumetric efficiency is 0.92. That's equal to Q actual divided by Q theoretical. Therefore, Q theoretical is Q actual 39.2 divided by 0.92. And that would give me 42.6. Again, just make sure this one you should get. So don't multiply by 0.92. I said make sure that always Q theoretical is higher, it's larger than the actual. Okay, so that might be a help if you flip those for some reason. With that, I can go back to my definition up there. So 42.6, that's Q theoretical. And that's equal to VD times 1800 RPM divided by 231. Therefore, the displaced volume is divided by 1800. That would be 5.47 cubic inch. Okay. I'll just discuss part B, but we'll solve it next time. It's kind of like it's going to take more than 5 minutes. But what we're looking for is we need to find the horsepower required to drive the shaft pump. So that's P inlet into the pump. You have two options. You either can use the the mechanical efficiency to calculate that or the overall efficiency? Both of them, they were, let's say the mechanical, it was P for the pump times Q for the pump. Again, that's the main difference. Divide by 1714, divide by Tn over 63,000, or that's what we call the shaft power, correct? Why is it stuck? We said that's where the right here. That's the mechanical power or the shaft power N required to turn and deliver that PQ over 1714. So that's what they're asking you to do, is to find that power, the horsepower required to drive the pump shaft. So we need to find this. Now, if you want to use the mechanical, then make sure you use here the theoretical value. And we have both. We have the actual and we have the theoretical. So it's up to you. If you want to use the actual, then make sure that you use the overall efficiency. We do have the volumetric and the mechanical efficiency, so I can find the overall efficiency. That's not the hard part. Otherwise, I could solve it. But the question is, because I do have this part, I do have Q's, the question is, what's P of the pump? What's the pressure needed or created by the pump? It's the delivery pressure. So we did this in chapter 1. It was the last example that we did, similar to it, not exactly that one, but it's this pressure, so 75, and then I reached to here. We did the actual line pressure drops with the DCV. We did it last time. So you have that pressure, and then it goes to here, and then we have to do the force balance here so that we can equalize between the left and right side so that I can calculate this P right here. P at the cap. So I'll need to do the balance between left and right. So F from here equals F here plus F load plus F friction if we have any friction. I don't believe we have any, but I can calculate P cap based on the pressure here and the pressure back to the tank. So if we do that, then I should be able to go trace that pressure all the way back to the pump. We will do it next time. So we'll stop right here. Let's keep this so that I know we stopped.